Okay, so last time we got to this famous slide where we substituted linear motion quantities x, v, a, and t with rotational motion quantities such as theta, omega, alpha, and t. And we did the same thing for the equations for a constant acceleration motion. So again, remember, we use this only for constant acceleration. If the acceleration is variable, then you really can't use these equations. And by a similar manner, we just substituted the kinematic equations with ones that work for angular motion. So v equals v0 plus at becomes omega equals omega 0 plus alpha t. So I'm just substituting v by omega everywhere, a by alpha, which is the angular acceleration, as you can see in this table, and so on and so forth. So we have these rotational motion kinematic equations, which we can use in any problem solving involving rotational motion with a constant angular acceleration. Now, what we did next was we were trying to link the angular quantities to the translational ones. Namely, we started with the fact that, so we took this example, we had 5 skaters and they were just moving in a manner such that they're all staying next to each other as they skate. So one will be fixed. This is the first skater here. You can see my cursor, right? It's tiny, but I'm hoping you can see it. Can you see my cursor?
Yes, I can see it.
Okay, let's see if I change it to this one. Can you see it now?
Yeah.
Yes.
All right, great. Yeah, so I have these 5 skaters. They're skating in a manner such that they stay side by side as they move. And to keep them moving while they are staying side by side, and they're not moving in a linear motion, they're moving through a circular path, they would have to cover the same angle theta. Do you all agree? Like this angle it's by itself this angle, right? It's the angle covered by the second skater. It's the same as the one covered by the third, fourth, and fifth. So in fact, these 5 must move in the same angular motion. But we noticed last time, if you look at the translational aspect of this motion, so when the objects are moving, if I look at the actual distance they cover, we said that the skater that is furthest from the stationary skater is going to move at a larger arc. So S for this skater is larger than S for the other skaters, as you can see here. Although omega is the same, theta is the same, the angular quantities are the same, but the linear quantities are not going to be the same, namely because the fourth skater covers a larger distance and they are all moving together, so the time is the same, then the speeds are going to be higher for the one that is furthest. The further skater has to move at a larger speed. شوفوا the speed vector here is bigger than the speed vector here, the velocity vector. So they will have to go at a larger velocity just in order to keep up with the skaters that are closer to the pivot point where they have to like cover less distance. The ones closer here have to cover less distance so they can go slower than the ones that are further away. And we also showed this mathematically with the below formula. I said that this skater has covered an actual translational distance S, which is the arc itself. This is the distance that the skater has covered. According to the angular or rotational aspect, this skater has covered an angle theta. Now from math, I know that this angle theta is equal to S over the radius, where the radius is the distance to the pivot point, so it's the radius of the circular motion that is going. So I know mathematically that S is equal to theta is equal to S over R. Are you all familiar with this formula from math?
Yes.
Theta here is equal to the arc length over the radius of the circle. So now all I'm gonna do, so this basically gives us the first link, which is between theta and s. What I will do next is I will look at my formula of omega and try to also find a relationship between omega and v, which is the linear speed, right? So who can remind me of the formula of omega? Omega is the angular speed. What's its formula in terms of the displacement?
Professor, is it delta theta over delta t?
Excellent, Jamal. Correct. Let's see if Adam Nuruddin can repeat for us as well. Adam, I'm gonna be randomly taking
Yes,
participation grades for
Professor.
our 10%.
It's delta
Yeah,
theta over delta t.
excellent, Adam. Yeah, so this is our formula, delta theta, or theta. Usually we substitute theta itself over delta t. Let's substitute theta here. We will get s over r delta t. Adam, what do you think we can do with this formula next? I remind you, I'm trying to find a relationship between omega and the translational speed.
Professor, I'm not sure, but aren't you trying to put it in terms of the displacement or I forgot the name of it. I'm not sure, Professor.
I'm trying to find a relationship between omega and v, where v is the linear speed.
Professor, I'm not sure what to do here. Can't we put it in another formula?
There's something we can substitute. Who can help us?
Is it the V over R?
Yeah, exactly. So, and was that Angela?
No, Miss Sirena.
Okay, thank you, Serena. Thank you, Adam. So what we are gonna do is we're gonna substitute S over delta T by V, and then I got this relationship. Omega is V over R. The angular speed is none other but the translational speed over R, which is the radius of the circular motion. And by a similar manner, alpha is delta W over delta T, and delta W, I just saw that it's V over R, and delta V over delta T is A. So I got that alpha is A over R. These three equations, they link the angular motion to the translational motion. Now I want you to be careful about something. The speed that we have found here is basically the tangential speed of motion. Now, speed is always tangent to the curve. So this speed that I will be drawing here, I will always write it as Vt, V tangential, because it's tangent to our circular path. So in angular motion, there will be some curved paths and the velocity will be tangential. Now, one very important thing is velocity is always tangential, by the way. So it's really ما هقول V tangential and V centripetal. Because if there is a centripetal or towards the center direction, the object would be also moving towards the center, which is not the case. So V is
Professor?
always tangential. Yes.
Sorry قطعتك بس I have a question. نحن بالكاينماتكس بالequations مش بنعتبر الألفا هو acceleration.
Yeah, true.
طب كيف اعتبرنا إنه ألفا equals A over R؟ إنه غلبطتني ما فهمت.
I wrote alpha as true.
Acceleration over R.
Yeah. So alpha is the angular
إنه can we
acceleration.
also consider this as well?
Yeah. So the thing
okay.
is, Jamal, I previously wrote my angular quantities in terms of each other. يعني كتبت alpha هي W over T and so on. All right. So I used these. Then I decided to link these to these or these to these.
Okay. I get your point. Yes.
So yeah, we're just trying to link angular quantities to translational quantities. And I want you to be careful. Like we said, V here is the tangential velocity, which is the tangent to the path. The velocity is tangent to the path. But the tangential velocity accelerate. Now, a tangential and a centripetal, where I'll now define a tangential to be a alpha times r or delta v over delta t. Now, who can remove of the centripetal acceleration? We talked about it in uniform circular motion. This object here, the skater, as he is moving, okay, he is moving on a circular path. I can define his centripetal acceleration. One. So that centripetal acceleration motion.
Miss Professor,
In
sorry to
uniform
interrupt,
circular
but
motion. Yeah.
your microphone is lagging a lot. You keep cutting off, and we can't
Yeah,
like hear
I
your
can't
first
really
sentences.
hear well.
So now is two aspects for the acceleration to be a tangential and we said this tangential acceleration is what we just studied now. It is alpha r from this equation, and I'll write it as at is alpha r, and it's basically are you all this equation?
Yes, Professor.
Which one, Professor?
So we distinguished between two accelerations for the skater, the tangential one, which is based on the tangential velocity, and we wrote it right here. It's going to be alpha times r or delta vt over delta t. So it depends on the tangential velocity. But I want you also to remember from circular motion, we defined a centripetal acceleration. Actually, anything that is moving in a circular motion must have a centripetal acceleration. Otherwise, how is it going to be tilting its velocity continuously across the arc? Like this skater, their velocity was over here, then it got tilted a little bit, then tilted a little bit. What's tilting the velocity is the centripetal acceleration, essentially. Who remembers our formula for the centripetal acceleration from chapter 4?
4 pi squared r over t squared, or v squared over r.
Exactly, Saharayan, thank you. So we defined our centripetal acceleration in circular motion to be v squared over r, which we also wrote in terms of the actual circumference of the circle, 2 pi r over t all squared over r. So the first one is the more basic one, of course, because it's in terms of the velocity, similar to a tangential, which is in terms of velocity here as well. So a centripetal will be v squared over r. V is the tangential velocity, but I'll write it as a speed, right? It's a scalar. So now I will have these two accelerations existing for any object that is moving in circular motion. And you can see now how the angular kinematics are more convenient and easier to study when the motion is circular. Like defining angle is easier than saying we covered an arc length of 2.5 meters, and then you have no idea where the 2.5 meters are. Is it a full circle? Is it half a circle? Whereas if I tell you theta is 30 degrees, you immediately know that this person has covered something like less than quarter of a circle. So angular motion is more convenient. And even if you look at the angular acceleration, it's just alpha. It's the rate of moving, of changing the angular velocity, and that's it. But if you want to go to the translational aspect, you will have to define a tangential velocity and then distinguish between two accelerations that the object will have. Rather than just defining the angular acceleration, which is sufficient here, you have to define the tangential acceleration and centripetal acceleration if you want to look at the translational quantities. Is this clear? So we can solve an example so you can see how I can ask you for either one of the two. Let's look at this question. A helicopter blade has an angular speed of 6.5 revolutions per second and an angular acceleration of 1.3 revolutions per second squared. For point 1 on the blade, find the magnitude of the tangential speed and tangential acceleration. So one thing you should notice is I had to select a point to define translational quantities. I can tell you the blades are moving with a speed 6.5 revolutions per second. This will apply to any point on the blade. As you can see, similar to the skater's case, all of these points are going to cover the same angle together because the blade is moving as a whole. But if you want to look at the arc length, the points that are further from the pivot point or the center or the axis of rotation are going to be moving at a longer arc and will have a larger tangential speed compared to the ones that are closer. So if I want to study tangential speed, I have to select the point at which I want to measure the tangential speed. It will depend on the location, whereas the angular speed is just the same everywhere. So yeah, we're interested in point 1, which is right here. Notice how point 1 is 3 meters from the axis of rotation. And this 3 meters is none other but which quantity? Emmanuel, can you tell us?
I'm sorry, Professor, can you repeat what the question?
Yeah, sure. So I'm saying this distance, 3 meters, is what? Like, is it V? Is it S? Is it R? I used this formula so far.
It's S.
So this is this S, the 3 meters?
The radius.
Hmm?
Is it the radius?
It's the radius, exactly. Yeah, that's correct. So this distance is basically what I will substitute for the radius. And this quantity, what is it, Emmanuel? What do you think?
It's
This
angular
6.5.
angular speed.
Yeah, this is the speed. And is it a constant speed? Are the blades moving in a constant speed?
Yes.
Well, I disagree with you.
No, miss.
يصير في angular acceleration.
Yeah, so Amir pointed out that we have an angular acceleration, which means that omega cannot be constant, Manuel. All right. So yeah, just continuing with the question, you would notice there's an acceleration, so this omega has to be changing. Okay. So yeah, and thus I will label this as omega 0, and I will label this as alpha, of course. Yeah. So what do we want to find? The tangential speed and the tangential acceleration. What I did was I have omega and I want the tangential speed, and I can write that as r times omega. There's a mistake here in the symbol. So I used v equals omega times r. That's what I used. I know omega is 6.5, and I have r is 3 meters for 0.1. Now what remains is just the fact that I have here revolutions per second, whereas here I have meters, and revolution is really a full cycle. I can find that so that, well, it's better to find it in radians. Radians is unitless, but revolution is not. How do we convert this to radian? I know one revolution is 2 pi radian. So 6.5 revolutions will be how much in radian? I just have to multiply these two. So all you have to do is multiply by 2 pi, then by 3. Tangential speed in meters per second, as you can see here. So I multiplied omega by 2 pi, found it in radian per second. Radian is a unitless quantity, whereas revolution is not. So if this is unitless, you end up with meters per second, the correct unit for speed. This is my angular speed. And then I want also the tangential acceleration. That's very easy. I have the angular acceleration, and A tangential is going to be alpha times r. So I'll just put 1.3. Again, this is revolution per second squared, so I'll multiply by 2 pi again, and r is 3 meters. You can find the tangential acceleration. Now I can ask you to find the centripetal acceleration also, and this is going to be none other but v squared over r. So the speed that you found previously divided by r, you get the centripetal acceleration. Any questions here? And one thing I wanted to see about the centripetal acceleration, which we wrote as v squared over r, v is v tangential always, because the velocity is always a tangential quantity. It will not have other components other than the tangential one. And we found previously that v tangential is r omega. So I can actually write the centripetal acceleration in terms of omega. I can link it to the angular velocity. And I have this new relationship for a centripetal. So if I add for you here part C, find the centripetal acceleration. Anthony, would you help us? Anthony Haddad.
Yeah, Professor. Yeah. We
Okay.
use the equation for centripetal acceleration v squared over r.
This is v squared over r. What is r in this question? We're studying point 1. So we use it everywhere. It is 3 meters, all right?
Yeah.
So this is 3 meters. And what do I substitute for v?
R omega.
Okay, I can either use r omega, or I already found it here. It is 122 meters per second. So I'll just use 122 squared over 3. That's it. Now, if I didn't calculate tangential speed before, and I was just, من أول part you were asked to find AC, then it's a good idea to use the second form of my equation, which is r omega squared, because I have omega given. Okay, so then I would use r omega squared. So I can write this is 122 squared over 3, or I can use AC equals r omega squared, and this is 3, and omega was 6.5 times 2 pi. That will square that as well, and you will get exactly the same answer. Thank you, Anthony. Any questions, everybody? Okay. So I have some more examples here, but you can take a look at them by yourselves. I'm going to move on to talk a little bit about energy. So I'm going to now define an angular kinetic energy. So this will be the kinetic energy stored by rotation. Now, of course, energy is just energy. I can use translational quantities. I can write K to be half mv squared. But remember, because the blades, for example, for the helicopter were moving with different points having different velocities, namely here v tangential is compared to v tangential at this point, points 1 and 3 will not have the same tangential velocities. So, Celine, can you tell us which velocity is larger? Is it v3 or v1?
It's v3 because it's further away.
Excellent. V3 is going to be larger. So when I want to find kinetic energy, I'll have to differentiate between different points. Thank you, Celine. So I'll have to differentiate between different points, and I'll have to add up all of these.
Professor, Professor, your mic, please.
Yeah, sorry about that. So the velocity here at point 3 is going to be larger, and then I will have to account for the different points with different velocities. K will be half m1, where this is point 1, v1 squared plus half m2, so on and so forth. Now, what's annoying here, for a blade, for example, the mass is continuously changing. I cannot really associate a mass for point 1 here and then a mass for point 2. And then I will have to basically integrate. So let's try to change this into some angular aspect where I don't have to worry about different points having different quantities. So what I did was, one, I wrote V in terms of the angular quantity. That's my first step to get rid of the varying translational speed. Namely, V is equal to omega times R, right? I'll substitute this, and then I'll have M1 R1 omega, M2 R2 omega. Omega is the same everywhere. So omega is going to be the same. It will not have a subscript I, for example. And then I will just add half mi Ri squared omega squared. So what's changing now is the masses across different points and the radii, or the distance to the axis of rotation. Now this quantity here, I'm gonna define it as a quantity that depends solely, if you notice, on the mass and the position of the object. I will name this quantity the rotational inertia of a body with respect to the axis of rotation. It is constant, by the way, for a particular object. Like if I have a blade and I know the distribution of its mass and the distribution of distances to the axis of rotation, this is not going to be changing, right? Like these blades, if they move faster or slower, mi Ri squared is the same. It just depends on the object shape itself. This is basically, this rotational inertia is an upgrade of the mass. Previously, we used to write K to be half mv squared. Now, look at my equation. It is half I omega squared. I just substituted the mass by the mass times R squared, just to account for the distribution of the mass over different locations, which will affect my angular quantities. And I is dependent on the object only, the shape of this object. So the same object, however it is moving, it will have the same rotational inertia. Same object, moving.
Miss, sorry to cut you off. I don't understand what you meant by, so on any point of the blade, I will be the same.
No, that's not what I said. So what I did was, I said that different points on the blade are moving with different translational or linear velocities. I don't like that because I cannot really associate different masses for different points. So my equation for kinetic energy doesn't look so nice. I decided to make this kinetic energy in terms of the angular quantities so that I don't have to worry about different points and their different speeds. So when I substituted V by R omega, I got this equation. Are you all fine with that? I substituted V by R omega, and then I ended up with the summation of half M R I squared omega squared. Now, omega is the same for all points on the blade, but the different points of the blade are at different locations R and different mass M. Now, these will depend just on the shape of the blade, the distribution of the points. So what I did was I associated a name for this quantity, the mi Ri squared. I named it the rotational inertia of a body. It's basically a constant that depends on the distribution of the mass of the body over the full surface of the body. Now, what happened when I did this definition, when I defined I to be mi Ri squared, my equation for K looked way more similar to the translational version of it. So basically, it's just as if I substituted V by omega, and M, the mass, because how the mass is spread will affect my rotation. Because basically, if I have more mass here, then M3 is bigger, less mass here. So where the mass is located is going to affect my rotation. I'm going to associate a location in addition to the mass. And this location is embedded in this quantity, the rotational inertia I. And thus, the kinetic energy will look like this, which is very similar to the translational kinetic energy. And it's more convenient because omega is constant across all of the blades. I'll tell you this helicopter has a speed of 3.5 revolutions per second. That's it. It's the same at all points. I don't have to worry about the speed of each point to find the kinetic energy. And I'll just need I, which is basically the rotational inertia, which depends on the shape of the blades and their mass and how this mass is distributed. Now I'm going to show you, of course, the basic formula is the sum of the mass times Ri squared. So basically to really find it, you'll have to look at the mass at each point and so on. And you would have to integrate, by the way, in case of the blades, for instance. But I don't want to take you to out of integral study. That's why I'm going to actually give you the values of the rotational inertia to be just given to you as they are. I want you to take a look at this slide. So, of course, the most basic scenario is just a single point. If I just have, rather than the blade, I had this axis of rotation, and there's the single point that is moving around this axis, then this single point will just have I equal mr squared. Do you all agree? That's the simplest scenario. And if I have 2 points that are rotating together, or the 2 skaters in the previous example, then I'll just have 2 mr squared. Actually, it will be m1 r1 squared plus m2 r2 squared, because the radius is not really the same. These are the simplest cases. Now, for objects with some area and distribution of mass, such as the blades here, such as a plate that is rotating, or a rod, or a sphere, then I'll have to integrate the different masses across the different locations. Now, I don't want you to do this integration. I don't want you to take sophisticated math in this course. Although once you go to engineering, you will definitely take another physics course with a lot of integration. But let's leave that till then. So I'm just gonna give you the final answers for the rotational inertia. So basically, whenever you see a plate, for example, with dimensions AB rotating around an axis that passes through its center, our formula for the rotational inertia is 1 over 12 m into a squared plus b squared, where a and b are the dimensions of the plate. If I have a sphere, for example, and the axis of rotation is passing through the diameter, then I is 2 over 5 mr squared. If I have a rod, and the axis of rotation is passing through its axis, then I is half mr squared. And by the way, if the same rod is now rotating about an axis perpendicular to its axis, this is the rod axis. If the rod is now rotating like this, then the rotational inertia looks different. It's the same rod, same mass, same length, but the axis of rotation is different. Then the distribution of masses around the axis is different. Before, the axis was here, so the points were just around it here. Now, the axis is here, so basically the different points are moving, like this point is moving like this is moving like this. They are rotating around this axis in a different manner from these points, right? So the rotational inertia will look different. So the one thing that I want you to just know is the rotational inertia I depends on 3 factors. Who can tell us what these 3 factors are?
Professor, can you repeat the question, please?
Yeah. Majdi, you're around? Okay, let's do it ourselves. So my question was, what does the rotational inertia depend on? So one, I can look at the formula. It will depend on the mass.
Yeah.
Miss, and the distance from the axis.
The radius.
And the distance, which is r, of different points from the axis. And 3, there's
The
a third
shape.
factor.
Is it
Not really.
No, how the mass is distributed, if it's like concentrated in the center or on the ends.
And basically the geometry of the
No.
shape.
Not really, because that is already embedded in the integration of R over M. So the shape, the distribution, the density, how dense it is, close or far. But its factor, like I want you to look at
its length.
length.
No,
Yes.
it's axis of rotation.
Exactly, it's the axis. Excellent, Ryan. Look at scenario C and E here. Same rod, same length, same mass, but the axis of rotation is 1 over 12 here, 1 over 2 here. Solely because I changed the axis, the points around which, the line around which the points are rotating. The axis does not show directly in my formula, but as you integrate, the R values will be like different when you change the axis of rotation. I thank you so much for joining me today, and I'll see you next week.
Thank you,
Professor.
Professor.
Thank you, Professor.
Professor.
Thank you, Professor.
Thank you.